And then I would like to invite, I'll see if I can pronounce it in the right way, Eftihia Tzen. Is that right? More or less? I hope so.
Yes, it's correct.
Okay.
Thank you very much.
Thank you and welcome. And we hope that we will look forward to your presentation about wind energy, a power source for water production through desalination technology.
Here it is. Let's see if it's work now. Is it okay? Is it fine?
Yes, it looks very good. Thank you.
Okay. Hello, everyone from Athens. Thank you for the invitation in this conference and the opportunity to discuss the use of wind energy for the production of potable water through desalination. As it's well known, the supply of drinking water is an important issue in the economic and social development of a region, both in urban and rural areas. However, according to a recent report, 2.2 billion people still do not have access to drinking water. As we can see in the figure, a large amount of the water resources is consumed for agricultural needs, while a further increase for all the water demands, industry, domestic and agriculture, is expected for the coming years and up to 2050. So what we should do? Before any other action, and in any case, water conservation and proper water management is of vital importance. Wastewater reuse is an option to cover the agricultural needs, while desalination is a solution to cover drinking water needs. Water desalination has become a technological and economically viable solution to tackle the challenges associated with increasing water shortages. Speaking on commercialized desalination technologies, this categorizes to two main subgroups: the thermal processes, in which we have the multi-stage flash, the multi-effect distillation and vapor compression, and the membrane processes. Here we have the reverse osmosis and electrodialysis. Desalination in general is an energy-intensive technology, and in this table we can see, among other characteristics, the energy requirements of each one. Thermal processes are high energy consumers, demanding thermal and electrical energy for pumping, while membrane processes and mechanical vapor compression require only electrical energy. The solution to reduce the carbon footprint of the desalination plants is their combination with renewable energy sources. The matching of the two technologies is technically feasible, and several applications exist around the world. Their applicability strongly depends on site characteristics, such as available water resources and area's potential, on site remoteness, on the type of application, if it's off-grid or on-grid, and on water demands regarding the required quality and quantity of the produced water. Most of the existing RES desalination plants are pilot units of small scale. So we can see here that wind turbines can be used to drive mechanical vapor compression, reverse osmosis, and electrodialysis. Since RO, reverse osmosis for seawater or brackish water, is the leading technology because of its modularity, efficiency in all water capacities, and lower energy requirements in comparison with other processes, we will focus our attention in this combination. Wind turbines to drive RO units is the second most used combination following PV, photovoltaics, RO systems. Wind turbines can be also used in conjunction with other conventional or RES systems known as hybrid systems. Most of the existing applications concern off-grid small wind turbines to power seawater and brackish water RO, while only few applications exist on on-grid small and medium wind turbines to drive RO. Wind-driven desalination systems can be classified in two major groups. One group is comprised of systems in which the desalination plant and wind turbine or wind farm are connected to a conventional distribution grid, and the other is comprised of standalone or hybrid microgrid systems. In other words, small-scale systems not connected to a conventional grid. As we can see in the case of on-grid systems, any excess of the electricity generated by the wind turbine injected to the grid, while when the wind turbine is not capable to fit the RO loads, grid electricity is used. In off-grid wind desalination, the main challenge with the combination of the two technologies is the variable nature of the resource and the fluctuations in power supply generated. Since RO, as all the desalination methods, are traditionally designed to operate with a constant power input. Directly coupled systems without energy storage can cause lower quality and quantity of the produced water, which is an important issue when we have to supply water to the consumers, to a village or a town, and reduction of the membrane life. So to avoid these fluctuations, different energy storage systems may be used. In this figure, we see the configuration of an off-grid hybrid RO system, which consists of wind turbine, photovoltaics, a diesel backup, chargers, inverters, and the battery storage system. The power supply system has to drive the reverse osmosis loads, which are pumps, with the most consumed load, the high pressure pump of the RO unit. Of course, we have other loads like the booster pump, the produced water pump, and the brine discharge pump. For electrical energy storage, battery storage is an option that can mitigate both the short and long-term fluctuation of the RES, while flywheels and capacitors can be used for short-term storage. Several factors such as cycle life, efficiency, etc., differentiate the various energy storage technologies and affect the levelized cost of energy storage. In most of the existing small off-grid wind RO applications, lead-acid batteries were used. Latest generation batteries, such as lithium-ion batteries, offer several advantages: efficiency, long cycle life, but their capital cost is still high for such small applications. In this table, we can see several applications of wind RO for the desalination of seawater and brackish water. Most of them developed by research centers and universities. Just a quick view on several case studies. The first concerns a hybrid PV wind seawater RO system developed by CRES in 2001 within PAVET project. 3 cubic meters per day seawater RO driven by 900 wind turbines and around 4 kilowatt PVs. The system includes battery storage, lead-acid battery storage, full automation of the RO unit, energy and water management control, which is important in off-grid, but also, of course, in on-grid systems, and remote control operation. Of course, you can see here the cost is too high because in 2001, the RO systems were expensive, but also PVs were too expensive at these years. So here we have other cases are the wind RO systems developed by ITC in Gran Canaria within Aerogedesa in Aerogedesa project in 2004 and Sodama project in 2009. The project concerns the matching of a 19 cubic meters per day seawater RO plant driven by a 15 kilowatt wind turbine with and without battery storage. Finally, Sodame project results validate the need of energy storage and constant power supply for the RO unit. Regarding grid, small, medium wind turbines drive RO, there are only few applications as mentioned before. One application is in Milos Island in Greece, where a Vestas wind turbine V52 of 850 kilowatt drives three modules, three seawater RO modules of 1,100 cubic meter per day each. The wind RO plant covers the water needs of the island population. There is no need for water transportation to the island. The selling price of water from the company to the municipality is around €2 per cubic meter, since it is BOT project, it's a build, own, operate and transfer project. Today, after 12 years, and I think that the RO unit increased by it's about 4,500 cubic meters per day. Another grid-connected example is in Texas, a grid-connected 50 kilowatt wind turbine to drive in around 220 cubic meters per day brackish water RO unit, but also other loads. And then we have another example with the coupling of Enercon wind turbine E33 of 330 kilowatts to drive a brackish water RO desalination plant with a daily water capacity of 800 cubic meters per day. Mostly this system used for agricultural needs and of course for other loads. The final unit water cost of this system depends on several parameters such as the site, the wind potential, the feed water quality if we have to desalinate seawater or brackish water, on the RO water capacity and energy requirements. Of course, also there are other factors such as the available infrastructure and the availability of budget. So according to the existing application, the cost of water produced by wind RO systems is in the range of 3 to 7 euros per cubic meter for small RO units, less than 50 cubic meters per day. Seems high, but this cost can be easily compared with the cost from other water sources such as bottled water, or with the water which is transported by tankers or trucks, as it is the example, or as it was the example from the Greek islands, where the cost of the transported water reached the 10 euros per cubic meter. Now, regarding some economic information, few data on the economics of such systems, that for small wind turbines with nominal power up to 15 kilowatts, the cost is estimated from 2,300 euros to 4,000 euros, while for small medium wind turbines in the range of 15 to 100 kilowatts, the costs range from 4,000 to around 2,000 euros per kilowatt, which for this type of application is high. Regarding RO, seawater RO capital cost depends on the water production and the use or not of an energy recovery device. This device is connected to the high pressure pump and reduce the energy requirements actually of the RO unit. So as an example, for a seawater RO of 100 cubic meters per day with energy recovery system, the cost is around 1,100 euros per cubic meter. For an RO, seawater RO less than 20 cubic meters per day, the capital cost is range from 2,000 up to 3,000 euros per cubic meters. I should mention that the energy recovery devices are not available for all the capacity, so you have to design your system as it's possible to have energy recovery device. Sorry. So for brackish water RO units, capital cost is less than 500 euros per cubic meter for units of about 100 cubic meters per day. Here in the brackish water case, actually we do not use energy recovery device. Exists in the market, but actually increase the cost and that is not so efficient. So concluding, keeping in mind the climate protection targets and strong environmental concerns, future water desalination technologies around the world will be increasingly powered by wind and other natural energy resources. Barriers such as the high cost of small, medium wind turbines and of the energy storage systems delay the development and market progress of these systems. Their cost drop in parallel with the development of more efficient and low-cost small energy recovery devices for the reduction of the energy requirements of small RO systems will lead to sustainable off-grid wind RO systems capable to offer potable water at a reasonable cost. Thank you for your attention.
Thank you very much. It's a pleasure listening to your speech. Are there any questions for Mrs. Tzen?
I have a question, if I may.
Yes, you may.
First of all, thank you for a very interesting presentation. And I was wondering, have you taken a look at markets around the world? Like obviously there's a high capital cost, especially for small wind and things like that. But when people don't have any water, or just like when they don't have any electricity, for instance, then those kind of costs and even the cost for the water itself kind of pales in comparison to the need for the water. And have you looked at what markets might be available in the world that would be willing to pay that, even to get the whole process started? It's kind of like, you know, and then when more and more people see that, maybe the cost can come down, or is there, it seems like there would be a good market in certain critical emergency areas.
Yes, thank you for the question. Yes, it's real. It's a great market, especially in areas where they have water resources, but most of them are polluted, like Philippines, India, but also here in Greece and in our Greek islands, we have several problems of potable water. However, in these sizes, in small sizes and small scale units, they prefer to use photovoltaic systems. The cost is very, very low. And I can say that they do not trust the wind turbines because they are not sure for the wind potential. You know, it's in these areas, they cannot have wind measurements. So they try to understand what is the wind potential, you know, by finger. And it's a risk. It's a risk. The cost is high, but it's a risk because there is no measurements. So they prefer to have small photovoltaic units with batteries and RO. There is also some companies around the world that offer these small units, and probably it's a more stable source, the sun. Don't forget that in this market, most of the people lives in these areas are poor people. So they need someone to make a donation or to finance this, even if it's World Bank or UNESCO or whatever. It's how it works.
No, I understand. The reason I ask is one of the things that we have encountered that we did not know is when we talk to solar companies, that if they add a wind component, it can substantially reduce the amount of storage required. And so there is a savings on the battery side. And I don't know, maybe that's a point of leverage or something.
Yes, you are right. I believe on this case, because also we at CRES, the first unit that we installed and we examined was a hybrid one, as I mentioned. And this is true that it was a very, very good, efficient backup. The wind turbine, it helped us a lot, especially early in the morning when we start to operate the system and the high pressure pump and all these loads. It was very helpful that we have during the night wind energy to charge the batteries. Yes, thank you.
Yes. Are there other questions? Not for the time being right now.